What specific problem does the inductive moment matching (IMM) method aim to solve in the context of generative models, and how does it address the training instability often seen in diffusion models?
Inductive moment matching (IMM) aims to solve the trilemma of achieving high-fidelity outputs, efficient inference, and stable training in generative models, particularly addressing the training instability often seen in diffusion models. IMM introduces a stable, single-stage training procedure that learns generative models from scratch, allowing for one or multi-step inference without the risk of training collapse that is common in step reduction methods like consistency models. By operating on time-dependent marginal distributions of stochastic interpolants, IMM minimizes divergence between distributions at different time steps, ensuring convergence to the data distribution. The method's reliance on stable sample-based divergence estimators, such as moment matching, further enhances training stability. Notably, IMM has been shown to outperform traditional diffusion models in terms of performance metrics like FID, while requiring significantly fewer inference steps.
How does the proposed inductive moment matching (IMM) algorithm work? Please illustrate the mechanism step by step, detailing the role of time-dependent marginal distributions and stochastic interpolants in the process.
The inductive moment matching (IMM) algorithm operates by learning generative models from time-dependent marginal distributions of stochastic interpolants, which connect data distributions at time, t equals 0, and prior distributions at time, t equals 1. First, IMM establishes a mapping from any marginal distribution at time, t, to any marginal at time, s less than t, allowing for both one-step and multi-step generation. This is achieved by minimizing the divergence between distributions at intermediate time steps, ensuring that the distributions at S remain independent of the starting time steps, which is crucial for training stability. The algorithm utilizes stochastic interpolants to construct conditional interpolations, maintaining the marginal distribution at S regardless of T, thus enabling the model to generate samples efficiently. Finally, through inductive bootstrapping, the model learns to match the target distribution by recursively applying the one-step sampler, effectively allowing the model to improve its performance as it generates samples.
Can you provide a simple yet illustrative example to demonstrate the inner workings of the IMM algorithm? Walk through the main algorithm steps using this example to clarify its operation.
To illustrate the inner workings of the inductive moment matching (IMM) algorithm, consider a scenario where we want to generate samples from a data distribution, Qx, at time, t equals 0, data to a prior distribution, p epsilon, at time, t equals 1 noise. The IMM algorithm begins by defining a time-augmented interpolation, x_t, that connects these two distributions. 1. One-step sampling. The algorithm learns a one-step model that transforms the distribution at time, t, to any earlier time, s less than t. For instance, if we start with x_t sim q_t x_t, x, epsilon, we can sample hat x_s from the model distribution, p_st caret theta x x_t. 2. Marginal preserving interpolants. The algorithm ensures that the interpolants maintain the same marginal distribution at time, S, regardless of the choice of T. This is crucial for stability and allows the model to generate samples that are consistent with the target distribution. 3. Inductive bootstrapping. The model is trained using samples from previous steps. For example, if we have generated samples at R less than T, we can use these to refine our model for S by minimizing the divergence between the generated samples and the target distribution, Q_s x_s. 4. Objective function. The training objective is defined using maximum mean discrepancy, MMD, which helps in matching the moments of the distributions effectively. This objective is optimized iteratively, allowing the model to learn the correct data distribution. 5. Multi-step generation. Finally, the model can perform multi-step generation by recursively applying the one-step sampler from T to R and then to S, enabling efficient sampling from the data distribution with fewer inference steps. Through this process, IMM achieves high-quality sample generation while maintaining training stability, as evidenced by its performance on datasets like CIFAR-10 and ImageNet.
What are the empirical or theoretical benefits of using IMM over traditional methods like diffusion models and consistency models? List specific improvements in terms of efficiency, accuracy, and inference speed according to the results presented in the paper.
Inductive Moment Matching, IMM, offers several empirical and theoretical advantages over traditional methods like diffusion models and consistency models, CMs. Firstly, IMM achieves state-of-the-art performance with a Frechet inception distance, FID, of 1.98 on CIFAR-10 using only two-step generation, significantly outperforming diffusion models that require more steps for similar quality. Additionally, on ImageNet 256 × 256, IMM achieves an FID of 1.99 with just 8 inference steps, demonstrating its efficiency in generating high-fidelity outputs compared to the longer inference times typically associated with diffusion models. The paper also highlights that IMM surpasses CMs, which often suffer from training instability, by providing a stable, single-stage training procedure that avoids the careful tuning and regularization required by CMs. Furthermore, IMM's ability to support both one-step and multi-step generation through a single model enhances its flexibility and reduces the computational burden during inference, leading to a 10x speedup compared to other methods. Overall, IMM's design allows for efficient training and inference while maintaining high accuracy, making it a compelling alternative to traditional generative models.
How was the inductive moment matching method validated? Describe the experimental design, including the datasets used and the metrics employed to compare its performance with other generative models.
The inductive moment matching IMM method was validated through empirical performance evaluations on two datasets, CIFAR-10 and ImageNet 256 × 256. The experimental design involved comparing IMM's performance against various generative models, including diffusion models, flow models, and few-step models trained from scratch. The primary metric used for comparison was the Frechet inception distance, FID, where IMM achieved state-of-the-art results of 1.98 FID on CIFAR-10 using a two-step generation and 1.99 FID on ImageNet with only 8 inference steps. Additionally, the experiments demonstrated that IMM not only surpassed existing models in terms of FID scores, but also exhibited efficient inference capabilities, achieving a 10x speedup compared to some models while maintaining high sample quality. The results were further supported by ablation studies that assessed the impact of various design choices on performance stability and quality.
What specific results did the authors achieve using IMM in their experiments, particularly concerning FID scores on the CIFAR-10 and ImageNet $256 × 256 datasets? What do these results indicate about the performance of IMM relative to other state-of-the-art models?
The authors achieved a state-of-the-art FID score of 1.98 on the CIFAR-10 dataset using the inductive moment matching IMM method with a two-step generation process. For the ImageNet 256 × 256 dataset, IMM achieved an FID score of 1.99 with only 8 inference steps, surpassing traditional diffusion models and demonstrating superior performance compared to other models like DIT and SIT, which were evaluated under similar conditions. These results indicate that IMM not only provides high-quality outputs, but also does so with significantly fewer inference steps, achieving a 10x speedup compared to some existing models. Overall, the performance of IMM suggests it is a highly efficient and effective generative model, capable of competing with and exceeding the capabilities of other state-of-the-art generative frameworks.